Welcome back. Last time we talked about measures of central tendency and when the mean, median, and mode could be useful as single summary statistics for a distribution of values. Often, however, we'd like to be able to say something about the rest of the distribution, not just the average, the middle, or the most frequent value. We've already considered dispersion graphically. Kurtosis is a measure of dispersion that uses a normal distribution as its reference. The range helps us get a general sense of a distribution. The range is simply the difference between the maximum value and the minimum value of the variable within the observed data. But it suffers from the same problem as the mean. A single extreme value can dramatically increase the range. Instead, we most often use variance and the related standard deviation to measure dispersion. So let's take the two sets of data points I used to demonstrate measures of central tendency again here, and add another that has the same mean as the first, but only half the range. So we've got one set that goes $10,000, $20,000, $30,000 up to $100,000. The second is the same, but instead of 100,000, the top value is 100 million. And the third would be 30,000, 35,000, 40,000, 45,000, 50,000, and so on. The first of these is evenly spaced, fairly closely, around the mean of $55,000 a year of income. To find out the deviation, or the prediction error of any given case from the mean, the mean is our best guess to its value without any covariance. So to find out that deviation or prediction error, we could subtract the mean from that value. In this case, the deviations would have a minimum of negative 50,000 and a maximum of positive 50,000. Notice that the range of the variable is the same as the range of deviation. The only difference is that errors are shifted to be centered on the mean instead of 0. The same property holds for our data with an outlier, except that the range of deviations is nearly $100 million more. But we're not quite where we need to be yet. If we were to add up all the deviations, the sum would always be 0. Mathematically, this is true because we defined the mean as the sum of the values divided by the number of cases, so the sum should be the same regardless of how it's distributed. Luckily for us, squaring a value always makes it positive regardless of the original sign. So for each case, instead of error, we now have a squared error term we can calculate. Adding all of these up gives a sum of squared errors. That sum of squared errors is the basis for measures of dispersion and variability from here on out. And if those errors are calculated based on a mean, the sum is called variance. Distributions with outliers or influential cases, or that are just more widely spread around the mean, that is platykurtotic, will have higher variances than those tightly packed distributions. To convert variance to a more intuitive unit, we can take the square root of the variance, not the individual errors, but the overall variance. This is called the standard deviation, and it's analogous to, but not the same as, the average difference from the mean in the original units. So looking at our three example data sets, we could calculate the variance and standard deviation to each and see how the distribution affects their values. Some things to notice. First, variance and standard deviation can change even if the mean doesn't. Like in sets 1 and 3, both have a mean of $55,000, but the third has a smaller variance because the values are more tightly spaced. Second, increases in dispersion and/or the presence of outliers have stronger effects on variance because it's squared than standard deviation. So the relative difference in standard deviations will be smaller than the relative difference in variances. So for example, a difference of 2 standard deviations would be a difference of 4 variance. A small number of outliers can dramatically increase the variance, such as in set 2. Among other things, this destabilizes a sample mean and makes it much harder to tell when effects are artifacts of sampling variability, something we'll talk a lot more about later. So a couple final notes to help keep this in context. If the model section of your master equation, that is the outcome equals model plus error, if that model section is simply the mean, then variance is also directly related to the error term. In a multivariate model, the variance is what we try to explain using independent variables. And finally, you may have heard the term standard error, and you definitely will in the future. Standard error is not the same as standard deviation or variance, so be careful about your language. That's basically it for today. Error is how much of each case's actual value is above or below our best informed guess. Variance is the sum of the squares of these, divided by the number of cases for a population, or by the number of cases minus 1, the degrees of freedom for a sample. And standard deviation is variance that's been transformed back into the original units by taking the square root of variance, which is useful for interpreting dispersion substantively. Thanks, we'll see you soon.